A warm welcome to the youngest child in the FMI family of standards. This is about the eFMI standard, and Christoff Bürger will present it. So Christoff has a background in computer science, compiler construction. He works with Dassault Systems in Sweden. He's working on the Daimler kernel, and also there participated in the emphasis project, prototyping the eFMI tooling, and he's the responsible author for the algorithm code, model representation, and the GALEC part of the eFMI specification. This will be also a recorded talk, so please play the corresponding video.
The following presentation gives you a short overview about the new Modelica Association project, eFMI, its motivation, status, relation to FMI, and project organization. eFMI is a new standard for the collaborative development of embedded software solutions from higher-level models like physics models. Collaborative means two things: collaboration of different varying tools from different tool vendors to achieve this objective. And collaboration also means between the different stakeholders along this chain from a higher level model down to the actual embedded software. You can think of it as a bridge, bridging, for example, physics simulation world and the embedded world such that you can reuse your physics directly in the embedded software. eFMI has been developed in the Emphasis Research Project, whose results are now transformed to the new Modelica Association project, eFMI. eFMI is not some far-fetched vision. The eFMI standard and prototype tooling have been developed hand in hand along challenging application scenarios in the Emphasis Research Project. For an overview of the eFMI standard, we highly recommend our publication at the conference. You can think of eFMI as a standardized workspace for the stepwise development of embedded solutions for models. Such a collaborative workspace has to cover all the development steps that are required to go from a high-level physics model abstraction down to actual concrete embedded implementations. These are the implementations along the varying representations of the solution, the testing of each of these intermediate representations, and the integration not only between the individual artifacts but also the integration on the final embedded device. eFMUs support to that end varying model representations. We have behavior and reference results for testing captured in behavior model containers. We have the target independent bounded algorithmic solution captured in algorithm code containers. This is an intermediate representation for which a new language has been developed, GALEC. Then we have the final C code implementations tailored and optimized for the requirements of specific target environments, such as captured in production code containers. And we have the binary distributions and their build receipts that are ready for the embedded system integration captured in binary code containers. These varying containers means that different tools are working on a single eFMU to construct its final result. An eFMU is a white box, a development white box, which is a huge difference to FMI. To illustrate eFMI, consider the prototype tooling developed in the Emphasis project. We have some higher level means to model controllers and virtual sensors, for example physics models in Modelica, and respective tooling where we can develop such models and simulate them, like Daimler or Simulation X. These tools can be used to generate reference results to test embedded solutions, and these reference results are stored in behavior model containers of an eFMU. But this tooling is also used to generate concrete algorithmic solutions in an algorithm code container of the eFMU, Such algorithmic solutions are represented in a new intermediate representation called GALEC. These GALEC representation of algorithm code containers can now be used in turn by production code generators to produce C code that is tailored for the runtime environment and libraries of a specific embedded target. Tooling developed to that end in the emphasis project is CATIA SP, Target Link, and Scholar Congra. But we could also have tooling that takes production code containers and generates more refined production code containers like AUTOSAR Builder. AUTOSAR Builder, for example, adds code to integrate production code for the AUTOSAR adaptive platform and to generate binaries that can be executed on AUTOSAR adaptive. We also have test tooling like TPT and S3 that can be used to either execute binary code and to check against the behavior models we have, but it can also analyze production code to find if it is conforming to MISRA standard and other embedded and real-time requirements. Of course, we can also take the production and binary code to deploy it on a concrete embedded target. It is important to note that the starting point of any further code generation is the algorithmic solution, the GALEC program generated by modeling tools. For one algorithmic solution, many different production codes for varying target platforms and embedded runtime environments can be generated. And for a single production code, many different binary codes can be generated. GALEC is an abbreviation for Guarded Algorithmic Language for Embedded Control. GALEC is an intermediate representation well suited as code generation target for modeling tools and serves for embedded code generation. GALEC is an imperative language, it supports side effects, and it is causal. It also provides high abstraction level, for example, multidimensional real arithmetic, and a lot of mathematical built-in functions like sinus, cosinus, interpolation in 1D, 2D, and to solve linear equation systems. GALEC is safe, embedded, and real-time suited. That means its semantics guarantee an upper bound for every algorithm, that is, every program terminates, and that multi-dimensions are statically known and indexing is safe. It guarantees well-defined and never competing side effects. GALEC provides safe floating point numerics. It has guaranteed not a number propagation and automatic saturation of ranged variables. GALEC also provides an ordinary control flow integrated strict error handling concept. That means that we have guaranteed error signal propagation, which enables in turn delayed error handling. All in all, GALEC guards further eFMI tooling by providing these guarantees that are so important in the embedded and safety critical domain. To better understand the relation between eFMI and FMI, let us consider the development process of an eFMU once more. I already mentioned that an eFMU is a development workspace where many tools collaborate to develop the final embedded solution. In fact, such collaboration can be iterative. In the emphasis project, for example, the code analysis tool S3 has been used to analyze production code and find shortcomings that are not good enough for the embedded target platform. These in turn led to iterations to regenerate production code using different flags until it satisfies the target platform requirements. This means in general that at system integration time we can have additional requirements like memory consumption that may lead to iterative development of production and binary code. That in turn means that an eFMU may not be in a state where it can be simulated, because parts of it may be stale artifacts. For example, we have a newly generated production code, but no binary code is generated yet. or we picked another algorithmic solution and production code is missing or binary code is missing. Compared to an FMU, this means that an eFMU is maybe in an intermediate state of development and not be ready for distribution to consumers for simulation. We can, however, pick an eFMU that is in a final state where we have a ready code that can be used for simulation and wrap it as an FMU. That means we pick one solution when the eFMU is ready, when the iterative development finished, for example. And for this solution, we generate an adapter for the FMI interface and add an FMU manifest. The resulting FMU can then be distributed to any further FMI tooling. I'd like to take a moment to highlight that the tooling presented so far is not something hypothetical. It has been developed in the EMPhASIS project. All the tools mentioned so far have been extended with prototype support for eFMI. Note that these are not newly from scratch developed tools, but rather well-established tools in their respective field, like TargetLink for production code generation and Daimola or AIMSIM for physics simulation. Most of the EMPhASIS partners will continue their support in the new MAP eFMI. The objective is to hopefully provide tooling on the market in a timely manner. To achieve this objective, we like to apply a defensive, bottom-up, prototype-based strategy for the further development of eFMI. This means that new eFMI versions are only released when we have a cross-check toolchain with tests covering all features. That means all the eFMU artifacts are generated and consumed. We also would like to focus on providing corrupted or misbehaving eFMUs that have to be rejected by tooling. This is something we didn't focus yet on in the EMPhASIS project, but we consider very important because it fits our domain, safety. The innovation is in the tools, not the interfaces or standard. The only exception may be the GALEC language. And the novelty is that we actually make this happen to bridge this gap between high-level modeling down to the embedded software. Since such defensive prototype-based strategy already has been used in the EMPhASIS project, we have a good feeling that the first official version of the eFMI standard will be released at the end of this year. You can already have a look in the published Alva draft. For the future, we plan a 2-year release cycle. In the first year, we define the new features. That is, what is the new things? Why do we want them? What are the limitations? We develop test scenarios and prototype implementations. And very important, a feasibility study that the specification can achieve completeness of rules that can be reasonably implemented. In other words, somebody tries to develop the rules that are applied and plays the evil guy to try to break these rules and see how the toolchain can badly go wrong. In the second year, we like to focus on cleanup of the proposed features. There are no new features added, and if any feature is in doubt, it is cut out. That means in the second year, we write the actual specification, and we clean up and prepare all of the tooling provided by the Modelica Association Project eFMI to have it ready for release when the new specification is released. Tool vendors can use this time to clean up their prototype implementations used in the cross-checks, such that their tooling is ready for release together with the new specification. This also means we like to avoid minor standard versions. Such are only for bug fixes. We want to make sure that stuff really works before release. That means we hope that there is less need for bug fixing. You can think of this like versioning in formal languages like C or C++. We hope you liked our short presentation and got you excited for eFMI. As a new project, we are very much looking forward for your feedback and for new members. Thank you for watching.